الرحيم. في البداية يطيب لي أن أعبر عن ترحيبي الحار بضيوفنا الأكارم الذين شرفونا بالحضور والمشاركة في أعمال مؤتمرنا الدولي الأول لأكاديمية ريمار، والذي سوف يعقد يوم الأحد المصادف 13 من ديسمبر 2020 برعاية كل من الأكاديمية ريمار وعلى رأسها الدكتور عامر كبلان، والجهة الساندة للمؤتمر هي جامعة فلسطين التقنية، جامعة بلاد الرافدين، مدرسة الوطنية العليا للإحصاء والاقتصاد التطبيقي في الجزائر، كلية العلوم من جامعة ديالى، والمدرسة هي المدرسة العليا للاقتصاد في الجزائر. هذا المؤتمر نتيجة الظروف الحالية الذي يمر بها البلد سوف ينعقد في تركيا أونلاين، ونشكر يعني الحضور لهذا المؤتمر. طبعا هو مؤتمر خاص بكلية العلوم الصرفة بصورة عامة، وأترك زميلي الدكتور عامر كبلان لإلقاء كلمة لهذا المؤتمر. تحيته. تفضل يا دكتور عامر.
شكرا جزيلا دكتورتنا لكلمتك في افتتاح أعمال المؤتمر العلمي الدولي الأول للعلوم الصرفة والتطبيقية والتكنولوجية، وأشكر مساهمتك في إنجاح أعمال هذا المؤتمر كذلك.
شكرا دكتور.
ولو سمح الدكتور أبو ذر وكان معنا على الخط يبدأ، فليتفضل ويلقي كلمته، وكذلك يلقي أو يقدم بحثه في هذا في الجلسة الأولى لهذا المؤتمر، لو سمح مشكورا. الدكتور أبو ذر، لو سمح الدكتور محمد الحمداني معنا على الخط. دكتور محمد الحمداني.
وقع النت.
دكتور
نعم
محمد.
دكتور. نعم دكتور.
تفضل دكتور لو سمحت تفضل بإلقاء بحثكم مشكورين.
نعم. شكرا جزيلا دكتور. فقط عفوا دقيقة لي.
بإلقاء بحثكم.
تمام دكتور، فقط الشير.
نعم دكتور محمد، اكو عندك مشكلة؟ العفو
دكتورة، بس في الشير. لا ما عندي مشكلة، بس الشير.
نعم.
شير من يمي يمكن اعتقد.
نعم.
ايه
وفيديو ان شاء الله تفتح له ولا؟
بإمكانك تعطي شير من عندك دكتور، وأنا أوافق.
نعم دكتور. نعم دكتور، هذا الشير.
اطلب شير.
نعم. طلع لكم شير دكتور؟
نعم دكتور محمد طلع لي.
دكتور اوكي.
تفضل دكتور. نعم.
دقيقة دكتور محمد بس أقدمك.
نعم.
دكتور محمد الحمداني هو دكتور في علوم الفيزياء، اختصاص بلازما، فيزياء بلازما. طبعا دكتور محمد الحمداني هو أستاذ مساعد في قسم الفيزياء، تخصصه جدا راقي في علوم البلازما. حيلقي لنا بحثه المنشور اللي هو الالكترون density spectroscopic measurement in aluminum laser induced plasma. تفضل دكتور. طبعا هذا البحث هو مشارك من قبل دكتورنا الفاضل الأستاذ الدكتور علي عبد الكريم، والأستاذ الدكتور كاظم عبد الواحد عادم، وكذلك الأستاذ المساعد الدكتور محمد عبد الرضا الحمداني. تفضل دكتور محمد بإلقاء بحثك.
طبعا شكرا جزيلا دكتور هذا التقديم، وشكرا جزيلا أيضا لإتاحة الفرصة للمؤتمر، المؤتمر الأول مؤسسة ريمار، المؤسسة ريمار. نعم. أيضا شكر موصول إلى الدكتور عامر قبلان لإتاحة الفرصة لهذه المؤتمر، وأتمنى لكم الموفقية والمزيد من الإنجازات. بحثي هو الكترون density spectroscopic measurement in laser induced plasma. كان بحث مشترك مع الدكتور الفاضل الدكتور علي، الاستاذ الدكتور علي عبد الكريم، وايضا الاستاذ الفاضل الدكتور كاظم عبد الواحد. Abstract: plasma generated by 1064 nanometer pulse neodymium YAG laser with a pulse duration of 10 nanoseconds concentrated onto an aluminum solid target under vacuum pressure is examined spectroscopically. The temperature and electron density specifying the plasma are measured by time-resolved spectroscopy of neutral atoms and ion line emissions in the time period range of 300 to nanoseconds.
طيب لا تاكلوا ترى شوالك وجعك. والنبي محمد بيده ترى.
And actually, spectrograph to appear the plasma emission lines. The temperature is obtained using the spectral line comparison method, and the electron density is calculated using the star broadening method. The electron density is characterized as a function of laser pulse energy, the time range where the plasma is optically thin, and is also in local thermodynamic equilibrium. It's significant for the laser produced plasma, which is evaluated from the temporal profile of the intensity ratio of two aluminum lines, lambda 1 and lambda 2 and lambda 3. Lambda 2 586.781 nanometer. It is found to be from 700 to 1000 nanometers. Introduction. In the operation of pulse laser deposition of solid target, energetic species are emitted from the surface of the target. The energy reaches up to several hundreds of electron volts. In the plume, the removed particles undergo different chemical reactions by themselves, as well as background species. Laser-metal interaction has recognized many dimensions on the basis of laser deposition in fundamental studies and technological applications such as simple deposition, environmental monitoring, biomedical studies, generation of the microclusters, cutting, drilling, surface treatment, laser patterning, manufacturing of micro and nano electronic devices, and magneto-hydrodynamic generators, etc. Laser-induced plasma technique is relied on optical diagnostics of particular atoms and molecules by observing their emission signals from the laser-produced plasma. This technique is very easy as compared to many other types of elemental analysis methods owing to its straightforward experimental setup. Laser-solid interaction goes to the generation of laser-induced plasma after a number of energy conversions, leading to the energy of incident laser exceeds the ablation thresholds of the solid. The plasma ejectants are composed of a combination of atoms, molecules, electrons, ions, clusters, micro-sized particles, and molten globules. In case of ablation in vacuum, where ablated species show high propagation velocities, one of the predominant contributions to the spectral line broadening is Doppler broadening. This is because of the Doppler shifts, i.e. delta lambda D equal to lambda V sub Z over C. Due to the different particles in the plume showing various velocity parts, D sub Z in the direction of observation. The effect due to Doppler broadening can be ignored. Putting the spectrograph at its high resolution can reduce the instrumental broadening. Stark broadening of spectral line in plasmas can be attributed to collisions of charged particles, resulting in line broadening and peak wavelength shift. The full width at half maximum of a stark broadening line in angstroms without an ionic support can be written by the relation 1. This relation delta lambda sub 1/2 equal to 2W NE over 10 to the power 16 in unit of angstrom. This equation describes the full width of half maximum of a stark broadened line as mentioned before, where W is the electron impact parameter which can be selected for different temperatures. NE is the electron density. Electron released from the target have high kinetic energy and ionize ambient species through collisions. The species excited in such process as well as participates in various reactions. Thus, electron density and its spatial distribution besides those of the atomic and molecular numbers are significant variables. Much studies on the electron number density in the plasma plume have been achieved by using techniques like optical emission spectroscopy, the Langmuir probe, interferometry, and optical transmissivity. The emission spectroscopy has been highly applied due to its non-contact nature of a probing and the information accessible over a wide spectral range. The electron density has been calculated from the stark broadening of emission lines in the case of laser-induced plasma at low pressure conditions. The temporal characteristics of electron density has been achieved to estimate a three-body recombination rate constants and recombination time. The purpose of this research is to estimate electron density NE of plasma produced by Nd:YAG pulsed laser of aluminum elements, which can be used in many applications such as electro-optics devices and semiconductors alloys. Experiment now. Go to experimental setup. The target of the laser-induced plasma process was aluminum with purity 99.99900 and compressed under the pressure 10 tons to make it shaped like disc with a diameter of 3 centimeters and then centered in oven to temperature T for 2 hours period. Laser-induced plasma experiment was achieved under vacuum pressure of 0.1 millibar by using Varian DS 219 rotary pump. The beam of neodymium YAG laser with first fundamental harmonic frequency lambda equal to 1064 nanometer, 10 nanoseconds, 6 Hz, was concentrated onto aluminum target with quartz lens f equal to 10 centimeter. The target was fixed onto rotating motor speed 4 revolutions per minute to avoid fast clating. The spectroscope used to collect the emission radiation from the plasma was of the types Sirwit S3000 UV near IR. The laser-induced plasma experiment was performed at room temperature. Laser-induced plasma setup scheme has been shown in figure 1. Electron density of the aluminum ablated atoms were computed by analyzing the emission lines spectra of the spectroscope data. The aluminum target was ablated by 1000 pulses. The vacuum pressure was changed from 0.04 to 0.2 millibar. Also, the laser pulse energy was selected to be 800, 860, and 940 millijoule to study their influences on the value of electron density. This is the figure 1. This is figure 1. Shows the schematic diagram of the laser-induced plasma experimental setup. As you show, there is laser beam, lens, and target with the beam incident at angle of 45 degree, and also there's on the other hand, on the other side, fiber optic and the spectroscope, and also the chamber, the broad chamber. Results and discussion. In this experiment, we took various laser pulse energies, as mentioned before, 800, 860, 940 on aluminum sample. By using the spectroscopy and comparing with NIST database, we took certain peaks as listed in table 1 from the figure between the wavelengths and the intensity. Figure 2.4 or figures from 2 to 4. Figure 2 shows emission spectrum of aluminum plasma at laser pulse energy 940 millijoule. Okay, this is the figure, shows the intensity and wavelength, and there we took we choose the two lines 380.581 nanometer and 586.781 nanometer for finding the electron density. And this figure 3 shows emission spectrum of aluminum plasma at laser pulse energy 860 millijoule, and also figure 4 shows emission spectrum of aluminum plasma at laser pulse energy 800 millijoule. We use MATLAB program code and equation 1 of Stark broadening to calculate the electron density, and by taking the full width of the half maximum as shown in table 1. Table 1 experimental and results data. This is NE as you see, NE in centimeter cube minus 3, and delta lambda I2 I1 the intensity 1 the intensity 2, the lambda 2 lambda 1 in nanometer, and also finally the power of laser energy pulse, laser energy pulse in millijoule. The proportional relation between the laser pulse energy and the electron has shown in figure 5, as shown in figure 5. As we observe, as NE increases, or as energy of laser pulse increases, the electron number density increases also. This figure 5 shows the laser pulse energy versus the electron density. It's clear from the figure 5, that is, it's clear of the figure 5 of the previous figure 5, that as laser pulse energy increases, electron density increases too. It's a proportional relation. The dynamic fluctuation manner of the laser-induced plasma is confrontation for diagnostics, because the principal plasma quantities change in time and space. The continuum or bromostructuring happens where a free electron collides with another particle and makes a transition to another free state of lower energy with the emission of a photon. According to such behavior of the electron density, and in figure 5 versus laser pulse energy, is attributed to the absorption or reflection of laser energy by the plasma during creation, which relies on frequency. By increasing the laser radiation, more excited species, ions, and free electrons are obtained, and laser pulse interacts with these species, leading to further leading to further heating and ionization. It's observed also from figure 2 to 4 that the width of the lines was increased with the increasing of laser energy. In the plasma, the spectral lines were naturally broad, and the principal sources of the line broadening is Doppler broadening and the Stark broadening. It's obvious that the electron density has a maximum value in the starting region of the plasma and decrease toward the direction of expansion. Finally, a conclusion: Q switched neodymium YAG laser with its fundamental harmonic 1064 nanometer has been used to study laser-induced aluminum plasma and measure electron density. The emission spectrum of the plume of a plasma discover transition of neutral and single ionized atom of aluminum. The electron density has been calculated toward the axial position of the plasma plume. The electron density and temperature which close to the target are maximum. The impact of laser pulse energy on the electron density of laser-induced aluminum plasma has been verified. As the laser pulse energy increases, the electron density increases also. They are directly proportional. Spectroscopic measurements has been used to find the electron density by using the technique line broadening. Full with half maximum get the electron density choosing a wide atomic line of aluminum plasma excited atoms or neutral atoms. And finally, these are the references I depend on to in writing the paper. And finally, thank you for listening. Thank you very much. وشكرا جزيلا لكم جميعا لحسن الاستماع.
أيضا نشكرك دكتورنا الفاضل الدكتور محمد الحمداني على لإلقاء بحثكم.
شكرا جزيلا دكتور.
والحقيقة ما شاء الله بحث قيم ولغة رصينة. وندعو الأستاذ الدكتور أبو ذر لو سمح مشكورا أن يقوم بتقديم بحثه.
السلام عليكم دكتور.
وعليكم السلام دكتور أبو ذر.
السلام عليكم. الله
يسلمك دكتور أبو ذر، الله يحفظك يا رب. دكتور محمد ممكن إيقاف الشاشة لو سمحت؟
نعم.
تمام.
عندنا دكتورة سيناء والدكتور حيدر المحنة هم هسه.
السلام عليكم ورحمة الله وبركاته.
هذا اسم هند غانم، هو دكتورة سيناء تلقي البحث. تفضلي دكتورة.
السلام عليكم ورحمة الله وبركاته. السادة الأفاضل، راح نقدم البحث من كتابة حيدر جبار كاظم وعادل كاظم شاكر وأبو ذر غانم محمد. اسم البحث Evaluation of Structural Morphology and Self-Cleaning Properties of GOAG, GOSI, and GOZN Nano-Composite Thin Film Synthesis by Sperry Pyrolysis Technique. الترجمة مالته راح تكون التحقيق في الهيكلية والتشكيل وخصائص التنظيف GOAG, GOSI, and GOZN Nano-Composite وهي أغشية رقيقة مركبة بتقنية الانحلال الحراري بالرش. راح نتطرق للمقدمة. Graphene is تشكيل خصائص
تفضلي.
Graphene is a 2D one-atom thick carbon structure that has a structure similar to the honeycomb lattice. Graphene oxide is an oxidative derivative of graphene that is generated by oxidation of graphite powder. The most common method of production the graphene oxide is hammer method. However, there's nanoparticle accumulator during the synthesis process, which eventually result in loss of their properties at nanometer level. Since graphene oxide has a large surface area, it can be used as substrate for nano-compound. نستمر بالمقدمة Introduction, Composition and Direction of Graphene Oxide Surface with metallic nanoparticle and metal oxide such as AU, AG, ZN, PD or nanoparticle subcarbonate oxide such as ZNO and TiO2 to improve the performance this material for applications such as mechanical strength, material biochemical, and electrochemical synthesis. Photosynthetic lithium batteries is a solar cell nanocomposite made of nanoparticle-based carbon substances such as graphene oxide have been one of the topic intersects to recount research in science and energy. Introduction. These carbon substances have a very higher surface area than volume, making them stable for very practical application. In 2006, reported the first graphene nanocomposite graphene piloted composite. According to their result, distribution of graphene with polarities increased the electric conductivity of composite. In the study, we intended to the prepare of GOAG, GOSI, and GOZN nanocomposite thin film by separate process method and invented the effect change in nanoparticle on the structure and weighting of this thin film. هنتطرق للطرائق الميثود. Construction of GOAG nanocomposite graphene oxide GO was depressed in an ultrasonic path for 0.5 hours. Silver diamond hydroxide solution 40 ml was prepared using ammonia, silver nitrate, and diazotite water. DI. GOAG nanocomposite was prepared by mixing the AgNH3OH solution and the graphene oxide solution and saturated for 0.5 hours. The final solution was then saturated in the oil path at 70 to 80 Celsius for 30 minutes. It was synthesized with DI water to remove the adylation material. Preparation of GOSI nanocomposition, ethanol and 10 ml of graphene oxide were mixed with this treated silicon 2 ml was added to the GO solution and saturated of the octanol solution was diluted by adding DI water and aged at room temperature for 1 day. Preparation of GOZ and nanocomposite. The graphene oxide GO was dispersed at the ultrasonic path for 0.5 hours. Examinated ammonia HAMTA solution 0.2 ml and zinc oxide solution 0.2 ml were prepared and mixed with GO solution for 50 minutes. The final solution was placed in the oil pot at a temperature of 90 Celsius for 3 hours and then centrifugated 3 times with DI water to remove excess solvent. Preparation of nanocomposite thin film using superior parallel device. At first, the class substances were washed by Acton. Then the separates were placed in the ultrasonic bath for 0.5 hours in order to prepare them film using superior parallel device 35 ml of each GOAG, GOSI, and GOZN solution were separated by compressed air as carrier gas. The nozzle distance was calculated about 30 to 40 centimeters. The deposition rate was chosen of 2 to 2.5. The hot plate temperature was set as 150 Celsius for GOAG thin film and 400 for GOSI and GOZN thin film. Now characters. X-ray different XRD device. The advised Precker YT model was used to confirm this composition structure of the synopsis in layers. Using CUKA precipitation at lambda 1.5418 at 2 volume between 5 degree and 80 degree field emission scanning electron This kind of model was used in visualization the surface morphology and obtained layers atomic force microscope AFM manufacturing by area research company were used to examine surface topology and of the layers. The measurement of contains angle of water droplet on layers under obtained condition at 25 Celsius was performed to measure the self-cleaning properties to the sample. Water droplets were placed in 3 different positions for each sample and mean the consider as the consist angle. Now, result and disconnection. We have the figure 1. Explain about X-ray Z diffraction spectrum of GOAG, GOSI, and GOZN thin films prepared by Sperry-Palazzo method. And figure 2 explain about the result and disconnection image of GOAG, GOSI, and GOZN thin films prepared by Sperry-Palazzo method. Figure 3 AFM image of GOAG, GOSI, and GOZN thin films prepared by Sperry method. Figure number 4 consist angle of GOAG, GOSI, GOZN thin films prepared using Sperry-Palazzo method. And the figure 5 comparison of consist angle of GOZN thin films using Sperry-Palazzo method. Conclusion. At the end, in this paper, the sole content of GOAG, GOSI, and GOZN nano-composites were prepared using simple method and were devised by Sperry-Palazzo technique. The effect of changing the nanoparticle on the structural morphology and weighting properties of this film is studied. The result of XRD spectrum show that is in addition to peak of RGO further diffraction peaks RC that are related to the AGSI and AGZN nanoparticle. The presence of GO sheet AG, SI, and ZN nanoparticle is also clearly evident in films. And AFM image the consist angle between the surface of him films are and the water drop was measured by digital camera. And among of the studies samples, GOZN nano-compact thin films, which has the lowest drop according to AFM result, also has the lowest CA and SI relatively good hydraulic surface. And thanks for your listening. It's enough.
شكرا جزيلا دكتورة سيناء. شكرا دكتور حيدر، وعذرا دكتور عامر كان اكو خلل موجود وما طلعت الصورة بالبداية مال باوربوينت.
تمام دكتور تفضل.
عفوا دكتور عامر.
بالاخير ظهرت الصورة دكتور.
اكو خلل موجود عذرا يعني على الخلل الموجود، لكن الدكتورة سيناء والدكتور حيدر المحنة والدكتور عادل هم اللي كانوا موجودين باسم هند موجودة.
نعم.
من سيقدم الآن دكتور أبو ذر؟ من سيقدم الآن دكتور أبو ذر؟
دكتور غصون الترتيب. أنا بالنسبة لي هو البحث أنا والدكتور حيدر والدكتورة قدمته الدكتورة سيناء،
تمام. دكتور عامر أرسلت لك باوربوينت الدكتورة سهى وطالبتها مسجل، تقدر أنه تعرضه؟ يعني لأن ما فاتحة حاسبة، أو أنه دكتور أبو ذر تقدر تعرضه؟ أنه أرسلته لك على الواتساب.